Sometimes we need to take the derivative numerically, and a centered difference approximation is usually the most accurate way to do that. If you recall our original definition of the derivative, we had f prime of x was equal to the limit as h goes to 0, f of x plus h minus f of x divided by h. So here we're only doing a difference from the right side. A centered difference approximation says we should do it symmetrically from both the right side and the left side. So the new definition of the derivative would be f prime of x equals the limit as h goes to 0. We would have an f of x plus h minus an f of x minus h divided by the width here. Now the width becomes 2h instead of h, so divided by 2h. And if we wanted to take the derivative numerically, we would just take h small and then do this center difference and divide through by 2h. We can ask then, how do we take the second derivative numerically using a center difference approximation? Well, we can let's start with the first derivative. So we have f prime of x equals the limit as h goes to 0. And instead of using h, let's use half of that interval. So let's use h over 2. So that would be f of x plus h over 2 minus f of x minus h over 2 divided by 2 times h over 2, which would be h. So we're going to begin with this first derivative formula. The second derivative then would be the limit as h goes to 0. And then we would need to take the derivative of f at x plus h over 2 minus the derivative of f at x minus h over 2 divided by h. Okay, so now what we need to do to compute the second derivative is use the top formula for the derivatives. So let me put it here. So if we compute the second derivative, we have the second derivative with respect to x is the limit as h goes to 0. So this is the first derivative. So instead of f prime of x plus h over 2, we're going to substitute this one, where x then takes the value of x plus h over 2. So we have f of x plus h, and then minus f of x divided by h. So that's this first piece. And then minus the second piece. So we're replacing x here by x minus h over 2. So that becomes an f of x minus f of x minus h divided by h. And that whole thing then is divided by h, this h here. So this whole expression is divided by h. This simplifies to the limit as h goes to 0. We have an f of x plus h. Then we have a minus f of x minus f of x. So we have a minus 2f of x. And then we have a minus minus f of x minus h. So we have a plus f of x minus h. And then all divided by, we have a division by h here, a division by h here, so all divided by h squared. And this is called the second difference approximation. This is called the centered difference approximation for the second derivative. F of x plus h minus 2 of f of x plus f of x minus h, all divided by h squared. It's exact in the limit h goes to 0, but if you're doing this numerically, then you would have some non-zero value of h. So let me summarize. If you wanted to do numerical work with derivatives, rather than using a derivative defined from just the right side of the function, we should center it around the function. That provides a greater accuracy in your numerics. The first derivative would be f of x plus h minus f of x minus h over 2h. And the second derivative would be f of x plus h minus 2f of x plus f of x minus h over h squared. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.